Welcome everyone to the first lecture in a series of 3 on the cosmic web. Today I want to set the scene, and tomorrow we will get into the dynamics of the cosmic web. And today already I want to sort of take a run up towards this and sort of introduce that subject. That will be a bit more complex than the generalities that I will present today. For those of you who were there tomorrow or were there yesterday for the public talk, some of the material you may recognize, but that will soon change. But of course, we first have to set the scene for people who are here today for the first lecture. So what we will be talking about is the largest structure in the universe, which is the cosmic web. A spider web-like structure that is pervading the entire visible universe and has a very complex constitution, in the sense that it is not having one particular scale. It does not have one particular recognizable shape. There are a range of different morphologies on different scales that are all connected in an intriguing network that is characterizing the large-scale meta-distribution on scales of a few up to hundreds of megaparsecs. So what it is can best be illustrated first by a fictitious simulation model. Computer simulations are too low to trade. We use computer simulations to basically follow the evolution of the cosmic meta-distribution, simply because the timescales involved are so vast, billions of years, up to 13.8 billion years, that we cannot wait ourselves to see this structure evolve. So we have to basically simulate it and ask the computer, given the matter distribution that we see today, how do you think it will have evolved under the force of gravity on smaller scales, also forces like pressure and a range of physical processes involved. What I first will show is introducing the topic, the kind of structure that we will be looking into. I will do so by a three-dimensional model, a computer simulation, so-called Cosmogrid supercomputer simulation, that is confined to a box, periodic box, of 30 megaparsecs. Not too large, but it illustrates us the main points. In there are 10 billion dark matter particles. And these dark matter particles were given a distribution in line with the Lambda CDM cosmology, right? Cold dark matter in conjunction with a cosmological constant of around 0.7. This was set to work and evolved for 13.8 billion years. Subsequently, we are going to look at the pattern that the dark matter assumes in this box. Now, I could show this in a full three-dimensional box, but that's usually very difficult to appreciate a full three-dimensional view. So one way of going around this is to show the distribution slice by slice by slice, starting from the bottom of the box up till the end. And then use your own brain to basically couple together the slices as they are to build up a full three-dimensional view, as if you're looking at the CT scan of the universe. So the first slice, two-dimensional slice through this box, you see on the background. The coloring is telling you the density, the local density of the mass. If it's white, it's a very high density. And you see, for example, here a node which would translate into a cluster of galaxies when in the observational reality. You see another one over there, and you see, for example, here a huge elongated structure. It's actually not an elongated structure because you will see that it basically goes on for various slices. So it's more like a planar membrane that is passing through the entire box. You also see lower density regions like you see over here. Black means low density. Lowest level here actually is around 10% of the average density of the universe. In there, if you look well, you see a lot of substructure. And a lot of that substructure is actually tenuous filamentary structures. So you see that you don't only have these elongated massive arteries, but also these very small ones. Now, what you also have to see is this might be a large underdense region. In that large underdense region, you recognize various smaller ones where you say, yeah, that's the boundary of a subvoid or something like that. That's a feature that we will actually look in more detail when we talk about hierarchical clustering. Now, when you look the various slices as we pass through it in the CT scan, you will see that sometimes these underdense regions start with small and then they expand and then they close again. That's not an evolutionary sequence, it is a spatial sequence. So you should see it that you're passing through a bubble, right? Mm-hmm. The same thing you may recognize for the filaments. Suddenly a very strong filament is popping up. Sometimes you see actually it prevails for a range of slices, and then you have a wall-like structure. At the same time, you see that these features happen on a range of scales. So as we pass through this movie, use your imagination to infer how the three-dimensional structure of this thing is. And that's a very good illustration of the kind of three-dimensional spider web-like network that we think of. Usually spider webs are more two-dimensional. This is more complex. It's fully three-dimensional. Okay? So let's have a view. So here you see basically passing through, and for example, here you see is a massive large void. Massive is the wrong word, voluminous one. And you see it's opening up, and in there you see a lot of filamentary structure on a range of scales. And you see that in those underdense regions, you see also networks. See here, there's a network showing up with nodes too, but it's not as massive as those nodes. Here suddenly the node disappears. But actually what happens is you're passing at that moment through a filament that is sticking perpendicular to this. And then suddenly you see huge conglomerations showing up over there. Also notice, by the way, that the high density regions never occur alone, right? Once you see a node, you see very close, a lot of them together. We call that clustering, right? They're clumping, they like to be together. Actually, when you look at the underdense regions and you try to infer the clustering of the underdense regions, actually they turn to cluster too. But that's another issue that we may talk about on Wednesday when we talk about voids. So when we look at this complex network, we may do a range of statistics. I mentioned this yesterday in public lecture. We will do a couple of more today, but let me first start with the basics. The first thing that we see is both the mass distribution as well as the volume distribution. So we do recognize four fundamental morphological features: filaments, walls, nodes, and large underdense voids. Doesn't mean that that's only four discrete possibilities, because there's a whole continuum in between them. There are filaments that are a little bit more flattened and stuff like that, but you know, you have to recognize and draw the line at some points. So you make a distinction: filaments, walls, voids, clumps. How much mass is in each? You see that 50% of the dark matter resides in filaments. So most of the mass in the universe is actually in those filaments. And of course, what you see, what your eye picks up, is that the filaments are the most prominent feature of the distribution of mass in the universe, as well as of the galaxies. We will see in a moment why that is, right? So that's the first thing you pick up. One of the reasons, of course, is not only because there's 50% of the mass in those filaments, but they also take in a rather small percentage of the volume, 6%. That means that the density contrast of the material in the filaments is pretty strong. So they're the first ones that you see because they assume they're basically everywhere, and their density is such that you easily pick them up. So your first impression when you look at the galaxy survey and maps like the Sloan Digital Sky Survey, it's filaments, right? Except then for the few clumps, like here the nose, which assume a much smaller percentage of the volume, they you saw jump out, but they're very localized, and they have densities in the order characteristically of 1,000 times the average density of the universe. The walls and the voids is another issue. They're not empty, but you know, voids is around 15% of the mass content in the universe, confined to more than 3/4 of the volume. So if you do the calculation roughly, you see that in voids typically 10 to 20% is the typical density inside the voids, right? With respect to galaxies, it's a different story. One of the last slides I will show you today is the kind of galaxies that are living in these different environments. And then we will see that actually the walls are hardly visible because they're populated by rather faint small galaxies, and voids even more. Okay, so that's the first. Then we may ask, okay, given that, can't we just simply assume a density criterion and say in between that density range, that's a filament? Well, it doesn't work. And you easily see that on the mark over here. Here I plot the density in units of the mean density of the universe and the PDF. So the fraction of mass that is living in those environments. Notice that this is a logarithmic scale. 10 to the 0 is the average density of the universe. 10 to the 3 is 1,000 times, typically for nodes. Now, if you look at the orange curve, you typically see that indeed the nodes are very high density features. But notice that in that movie I showed you, there will not only be very compact, thick nodes, but also these smaller ones. Groups of galaxies, we would say, like our local group. They are around here, right? So you have a whole continuum. Some of these nodes are extremely massive. They are actually the connections between the most massive arteries. But there is all this small scale stuff, and they are connected by much smaller ones. Now, voids are here. That's the dot dashed line. And they, as expected, usually have a density lower than the average density of the universe, with the exception of a few. That's basically the voids inside superclusters and very high density regions. It's not a lot of them, but some of them are there. Right? Here you see it. Now, again, the story of the cosmic web is mostly the story of filaments. And there you see the blue dashed line. You see that the densities in filaments are stretching over 5 orders of magnitude. Right? So that confirms the visual impression that you had of small, hairy tendrils, as we call them, inside voids, and the most massive connections towards the nodes. Those are the guys who even reach densities of almost 1,000 times the average. Right? So that's one statistic. What about some other statistics? Because up till now, I only mentioned the dark matter density, right? But you could do the same statistics with other components of the mass distribution in the universe. So here you see a few rings, each of the rings concerning another component of the cosmic mass distribution. We actually applied this to the Eagle hydro simulation that also includes galaxy formation. And you may ask, you know, what if I look at fictitious galaxies that are formed, and where do they reside? Or most of the atoms not being in galaxies but in the gas, whereas most of the gas in the universe. There's a group of astronomers who actually, when you talk about the cosmic web, basically mention specifically the gas distribution. And there you see the numbers. The outer ring is basically the dark matter. So you recognize the same, you know, 50% of the dark matter is in filaments. So you see the same numbers approximately in that simulation, but with, you know, 50% in voids. 25% in the walls. There is some difference from one simulation to the other ones, but on average, it's the same number. Now, interestingly, when you look at the gas distribution, the intergalactic medium, we see that it's approximately the same thing. It's not different than the dark matter. Around 50% of the gas is in the filaments, right? So this is the gas in between the galaxies, intergalactic medium. 70% is in the voids, right? In some form or whatever. With the galaxies, it turns out to be the same thing. It's around 50% of the galaxies are living in the filaments. Most of the galaxies that we, you know, the most common ones, like our Milky Way and the rather smaller ones, they are living in the filaments. Except when you look at the voids or the walls, we will see later on that the galaxies in there are all very small and faint. We actually even found this in the observational reality when we looked out in the Sloan Digital Sky Survey and looked for what was happening in the voids. We all found small blue little fuzzy blobs, very faint galaxies. So you won't find there galaxies like our own Milky Way. But interestingly, you could also ask, what then about the stars that are living in the galaxies? And then, actually, because most of the galaxies that, like our Milky Way, are in filaments, and they actually represent most of the stars in the universe, you see that the staggering, well, here it's 76%. When we look at illustrious, it was 80% of the stars live in filaments. That is, they live in the galaxies that are living in filaments. So most of the stars in the universe actually is in filaments. And that's not a lot for example, the voids. The voids here hardly assume anything in terms of stars, because it's only small, blobby kind of features. Okay, so setting the scene, very quickly going through some of the observational indications and for the observational objects. I would say that the first solid evidence for the existence of the cosmic web was already seen in the two-dimensional sky distribution of galaxies. Here is a very famous map. It was a map that was produced in 1978 in an article by Jim Peebles and Ray Sonera, I think Guido knows that even better than I do, but it's a beautiful map. And it's built on the basis of the so-called Shane-Wirtanen catalog. Now, for those of you who are used to the Sloan survey, which probably for your generation is already becoming an old-fashioned thing, and because you're more used to living in the future towards Euclid and those kind of things, and you're thinking in terms of batteries of CCD kind of detectors, this was the real work. What these guys did, counted for almost a decade, plate by plate by plate, photographic plate, with eyepieces, counting galaxies. Can you imagine every morning you go on bike to work, you step off, you start into your office and you start counting until the end of the day. You put your eyepiece aside and you go home again, and next day you do again, year after year after year. And then finally they published in the early 1960s 6 volumes, books like this. Nowadays you have to excavate them from some central library, I guess, but you know, even in my days, you could go to the library and find these books. And position on the sky, they had the numbers, the amount of galaxies. Now, that was real monk work, isn't it? Monastic work. Now, Jim Peebles took this in the 1970s, and he was a lot more modern. So he translated these counts into a beautiful map. And you see the map over here. So this is not photographic. This is not even photographic plates scanned. This was really purely numbers put there by hand. The story goes that it was his 3 daughters who did this as their summer holidays occupation. And I assume that Daddy was very happy with the fact that he wasn't bothered by the daughters having to entertain them, because they were very busy with their paint box, putting dots. But what you see is reality. What you see here, for example, this is the Shapley concentration. It's a well-known concentration with more than 30 clusters. And these huge nodes are all very well-known objects. But if you look well and use a little bit your, at hindsight, imagination, you see that it is actually the projection of a weblike network. If you ask Jim Peebles, he probably wouldn't agree on this, but I do see that. You know, you can see sort of filamentary connections between all of it. At least it is a clear indication that this is a clumped distribution, but not only just clumps, it is a really organized structures distribution, right? Quite different from the view that we have nowadays. This is the result of still the largest campaign of determining galaxy redshifts, the Sloan Digital Sky Survey, based on a real systematic CCD-based photometric survey, and in there the galaxies were automatically selected as galaxies up to a magnitude of 17.77, and then they took by fibers the spectra, determined the redshifts. And the map that we get is, as far as I can see, clearly one of a beautifully structured pattern, with us here at the tip, and in blue, light blue, each dot is a galaxy, and the contours is basically a density map, adaptive density map, based on those on that survey, and through a certain slice in the survey. The entire survey basically spanned almost a quarter of the sky, with over 1 million galaxies, and you clearly see a web-like pattern, right? You also see that the pattern is not one of one particular scale. You recognize features of various different scales. And a very interesting object, for example, is to look at the underdense regions that we also saw in the simulation. So here you see a circle that is centered on the so-called Boötes void. The Boötes void is the canonical example of a void. Now, we here have one of the discoverers of voids. Bido was one of the first ones. Was it 75, Bido? 75, right? But I think the penny dropped, rightfully, in 1981, when Kirshner and a few of his colleagues published a paper, very short paper, where they had actually, in a narrow beam, in the direction of the Boötes constellation, counted the number of galaxies as a function of redshift, and noticed there was a huge gap of 50 megaparsecs where they didn't see any galaxy. Everywhere at that moment, suddenly everyone recognized, hey, these voids, they are actually a systematic component of the universe, right? We now know of the cosmic web. They followed up in the 5 years after that, mapping that whole region, and they indeed find that when you look at the whole thing, it's a large empty region. But it's not completely empty, as you see from the Sloan survey, because you see inside that void are smaller voids. And actually, when you look at it on the sky, you would clearly see here, this is also from Sloan, that the whole thing is having a complex structure. So the void is underdense, but also contains structure itself, right? So that's the more up-to-date impression that we have of the galaxy distribution. Now, I did tell you that most of the cosmic web is dark matter, right? Because dark matter is the dominant matter component in the universe. In fact, what you can argue is that the galaxy distribution is nothing more than a sparse sample probes of the underlying dark matter distribution. But the dark matter you cannot see, right? So that's a bit of a problem. Now, you could argue, okay, that's forever. Later on in the week, we will learn from Henk Hoekstra that actually there's a way around this. You could look at gravitational lensing and try to infer the underlying dark matter distribution implied by the deformation of the galaxy images by the underlying dark matter. But it's taken a huge amount of effort, and the resolution is still not on a par with the galaxy distribution. However, there are some extremely smart people who devised extremely sophisticated data analysis pipelines based on very sophisticated statistical machinery, Bayesian inference techniques, and I may mention at this Francisco Di Taura, who basically started this game, his former student Jens Jasje, Guillaume Lavaux, they are really the masters of this topic. Now, what they do is they take the galaxy distribution observed and they wonder what would be the implied underlying initial matter distribution in the primordial universe 13.8 billion years ago, that according to our understanding of structure formation would have evolved in the galaxy distribution that we see. That's a probabilistic question. That's a range of realizations that would do it, but the more galaxies you have, the more you narrow down the possibilities. Every galaxy, like in Bayesian inference, adds new information. So they build a complete machinery around it, and that enabled them to reconstruct the dark matter distribution here in our local universe. That is the universe that was probed by the galaxy surface. No longer just the galaxies, but the implied dark matter distribution. And then you evolve it forward by your machinery with a simulation code or a description for how matter distribution evolves. And you wonder what would be the dark matter distribution in our local universe. You see it on the map. This is an iToF projection of the implied dark matter distribution around us. It's like you would look on the sky and you are suddenly able to see the dark matter. This is what you would see. It's like you are caught in the midst of a spider web. Look at the stunning resolution and detail implied by this machinery. And this is real, right? This is very close to what the observations imply of the underlying dark matter distribution. And one thing that you, for example, see is not only it's a fine filigree of filaments stretching all over the sky and stuff like that, but you also see that the dark matter web has actually a finer resolution than the galaxies that populate it. Of course, because it's much finer resolution, the galaxies are only discrete products. I always find this marvelous way of using your data and getting the optimal amount of information out of this. So I always have admiration for this kind of work. Now, another question that you may have is, okay, that's the dark matter distribution, right? But is that all the information? So do we have the galaxies that tell us about the underlying dark matter distribution? Or is there even more? Well, there's also the gas. And the gas, the intergalactic medium, is by far the most abundant atomic component of the universe. There's much more atoms in the intergalactic medium than there is in stars, in galaxies. Actually, I always like to insult my stellar astronomy colleagues by telling them that stars are of no significance in the universe whatsoever, just to provoke them, of course. But actually, in terms of inventory, it's true. I mean, main sequence stars like our sun are around a promille of the total energy content of our universe. For those of you to put things in perspective, we know that our galaxy has 200 billion stars. There are in the visible universe around 100 billion galaxies. You would think that produces a hell of amount of light, stellar light, right? Because stars shine and etc. It's nothing. All the photons produced by the stars in the universe, integrated over the lifetime of the universe, is a minor fraction of the cosmic microwave background photons. It's an afterthought, just to put yourself in perspective, right? So cosmology here presents. Now, going back to the subject is the atoms. Now, most of the atoms is in the intergalactic medium. And you see here an excerpt from the large illustrious simulation, which, you know, the whole machinery and the whole database of illustrious simulations at the moment is probably the largest database of simulations around in cosmology. And you see on the right-hand side that indeed the gas is also residing in the cosmic web. But you do see a marked difference with the web on the left-hand side. That's the dark matter. You see that the dark matter filaments are finer, slightly thinner than the ones in the gas. You also see that you see more substructure in the dark matter ones. Why? Dark matter doesn't have pressure. Gas does. So the whole physics of the gas is more complex. It makes the filaments a little bit more fluffy and stuff like that. But the advantage is you could potentially see that gas, right? It's difficult, but there are all kinds of attempts. For example, you could, for example, look out into the cosmic web and wonder if I look at a background object, like very bright one, like quasar, would the light coming from the quasar, could I see the signature of the neutral gas on the way towards us? The neutral gas resides in those filaments, and they were basically expected to absorb the light. It's very well known as the Limonov forest. And indeed, there are now huge campaigns, like, for example, the Clamato survey, where they look at many lines of sight. They look at the Limonov forest, the absorption of light, and they translate this into a three-dimensional map of the gas distribution at high redshifts. Sure enough, you see the voids in the filaments, in the gas. So that's another way. Still, the resolution is not huge. It doesn't have the resolution that we obtained from the galaxy distribution, but it's a very promising probe. Another one is looking at the most heavy filaments at high redshifts. We know that the clumps are filled with extremely hot gas. We know that actually clusters of galaxies are not clusters of galaxies. The best way to describe them is balls of hot gas, which you would see with an X-ray telescope, actually. That's how it actually got detected. That's what they first and foremost, the galaxies and the stars, as is thought again an afterthought. So actually, the hot gas in the clusters you can see in the X-ray, but not only in the X-ray, the hot electrons in that intercluster medium actually is able to give a kick, sort of content scattering, to the cosmic microwave background photons. They actually get kicked up to a higher density level, energy level. So they extracted from the lower energy ones and they are pumped into the higher energy ones. This was actually predicted by Sunyaev and Solovich around the year 1970. At the time, everyone thought that this was a beautiful piece of theoretical work and totally impracticable and unfeasible to ever be seen. And there you see it. This is a map from the Planck satellite. So you can see it in clusters. But the filaments, the bridges in between them, may also contain hot gas. Not as hot, because the density is not as high, but we saw that some of those filaments reach densities of around 100 times and slightly more than the average of the universe. So those are pretty hot guys, right? The potential wells are deep. So the gas that fell in got heated up. And sure enough, with Planck, they managed to find bridges in between, for example, this pair of clusters. So you can see the filaments, at least the heaviest ones, also in this Sunyaev-Solovich effect. And there are other ones. The nearby gaseous cosmic web, there the gas got heated up, but not to X-ray radiating temperatures, at least not hard X-rays, more soft X-rays, and the problem there is you can't see it. We call that the warm, hot intergalactic medium. You still have to look at very cumbersomely in absorption, but the hope is that at some point in the future, we will be able to look in the gas distribution. That would be fantastic because, like you see, the gas is everywhere. And we could map the complete outline of the cosmic web in the gas distribution. So that's some of the things that we could actually observe the cosmic web in. I won't say anything about gravitational lensing because you're going to have lectures by Henk Hoekstra on this, so he will be able to tell much more detail what you can do there. But also there, we have detected filaments in between two clusters in gravitational lensing. So there, that was basically the first direct view of the dark matter cosmic web. So how should I see the cosmic web in history? In what's its place in the development, in the history of the universe? So here is a kind of a timeline of the universe, with here, of course, the characteristic transition coinciding with the cosmic microwave background, the recombination transition. This is the early universe. In the early universe, there is not a lot of structure in the atoms. Dark matter starts to form structure, but the pressure of the baryon photon plasma prevents a lot of prominent structures to form. That, of course, changes 379,000 years into the Big Bang. From that moment on, gravity is able to mold the mass distribution that emanated from the early universe, the small, tiny Gaussian fluctuations, and gradually you start to see what the cosmic web is actually about. It's the first stage of structure formation following the primordial Gaussian circumstances. Gravity starts to mold these tiny fluctuations, 1 in 100,000, and makes them collapse, contract and collapse. And the first stage of contraction is actually the formation of walls and filaments. We will see later on what dynamically this is coming from, and that this implies why the filaments and the walls are connected up in a network with nodes at the nodes, clusters at the nodes. There is a dynamical reason for that. Now, the fluctuations in the early universe had a much higher amplitude on small scales than they have on large scales. That means that the morphing by gravity of those primordial fluctuations went much faster on the small scales than it went on the large scales. So the first stage of structure formation is on scales of stars and galaxies. So if you would look back 12 billion years ago, like we will now soon do with JWST, you would see a cosmic web, but it would be much smaller than the one of today. Right? Cosmic structure formation started to reside over there. If you would be able to see the remnants of what is around our galaxy, in a sense, you would still see the hairy extensions, very faint hairy extensions around our galaxy and all the other galaxies, the small scale cosmic web. But as time proceeds, gravity is also getting hold on larger and larger scales. The small structures that have formed are starting to climb into larger and larger structures as the structure on large scales starts to contract and collapse. So gradually, as time proceeds, we see that the cosmic web attains larger and larger and larger scales. And nowadays, after 13.8 billion years of evolution, we see a web-like structure on scales of a few up to hundreds of millions of light years, of parsecs actually. And that is actually now the scale at which we see the first prominent structure to form in the shape of filaments and walls and nodes. Someone asked me again, I think following a remark that I made yesterday, is, does that mean that there, in the future, there will be a cosmic web of a larger scale? And the answer is no. And I guess most of you must suspect what the reason is. Because in the last 7 billion years of cosmic history, dark energy started to dominate the dynamics of our universe, leading to an ever closer exponential expansion, the Sitter expansion. We're now really close towards that exponential expansion. And that means that the fluctuations on even larger scales will never be able to win again from the universe. They will no longer contract. They will no longer collapse. They simply can't win anymore. So the largest cosmic web that we will see is actually the one that we see today. You might ask, does it then always remain into the future? Someone asked me about that. The tentative answer is no, it will not dissolve. Why do I say tentative? Well, we once did the experiment with a simulation where we had the simulation run on for another up to an expansion factor of 100, so hundreds of billions of years into the future. And we had expected that actually the cosmic web would dissolve, but no. In 100 billion years, our descendants, who will then be alive, I don't know in what form, will look out into the sky and they will still see the same cosmic web. Locally, it may have looked somewhat different and evolved, but they won't see larger filaments, and they also won't see the disappearance of the filaments that we see today. So we live in a unique time in that sense. We actually are living in the time that we see the cosmic web that will be the cosmic web forever. Now, to give you a little bit of a, the movie already stopped, to give you a little bit then the impression of what I told you about this so-called hierarchical clustering, and we will get to that tomorrow in much more detail. So what does that mean? Well, you see on the left-hand side, that's actually a simulation that we made. What we did actually, we went back to a redshift of 2. We identified the matter that was actually living in the walls, in between the much smaller voids at that time. And then we followed where they ended up in the next 10 billion years, that is from redshift 2 up to a redshift 0. And you see that basically what you see is that these small structures merge together into ever larger structures. So it's a rather fine illustration of the hierarchical formation process. You see it also on the right-hand side. That is actually a simulation that was focused on a primordial filament forming. So you see here at a very high redshift of 9, you see a mass distribution that's a bit anisotropic, and you follow it in time. And what you see is the formation of small filaments. And then if you look well, you see that the small filaments start to merge together into ever larger structures, finally leading to a large massive filament that we see today. It's a whole complex process. For example, you see that the filaments are not going to be directed in one shape, but they basically get folded along the line of the dominant filament. So that gives a kind of the impression that you go from small scales to large scales, right? So that leads to the characteristics of the cosmic web. We saw all kinds of structures, and these are the 4 fundamental properties, characteristics of the cosmic web. So we saw a whole range of morphologies: filaments, walls, nodes, voids, all these kind of things. So we have a diverse morphology, and the dominant form is actually those filaments, anisotropic structures. And we will see that that's going to be a key property of gravitational clustering. It always first produces anisotropic features, not clumps, but anisotropic features. It's clear, you saw that from the hierarchical evolution, that this is actually producing structures on a wide spectrum of scales. So the hierarchical evolution leads to a multiscale structure in the mass distribution. That is, you have structures over a wide range of scales. Small scales over 10th megaparsecs up to hundreds of megaparsecs. And it is a result of this hierarchical building of structures. And then, of course, we see that the overdense filamentary features in the nodes are actually assembling most of the matter in the universe, but actually represent only a small part of the volume. So you cannot say anymore that the perfect symmetry that we saw in the initial circumstances, where 50.000% of the universe was underdense and 50.000 was overdense, that pertains. Actually, gravity is changing this. To state this in expensive words, the universe went from a Gaussian distribution to a non-Gaussian distribution. And if you consult the literature, you'll see that there's a lot of discussion about the non-Gaussianity of the universe. And actually what a lot of cosmologists are looking for is small deviations in the primordial universe from this perfect Gaussianity. It's a kind of a holy grail because it would inform us of the inflationary epoch. But as yet, no signature of non-Gaussianity has been found yet. So it looks like, to very good approximation, the early universe was perfectly symmetric between underdense and overdense and evolved into a wildly asymmetric distribution between overdense and underdense in the present-day universe. And then, in the end, we end up with all these components. And we may wonder, how is it distributed throughout the volume? It could have been scattered randomly, right? I mean, some filaments and some walls and stuff like that. But it's not like that at all. In the end, they are in an ordered system. Filaments always end up at nodes. Filaments are always tied in with walls. And the walls surround the voids. So they are all coupled together. They are all connected together. And this is a word that by now in the literature starts to be more and more mentioned. It's the aspect of connectivity. To understand connectivity, we probably need a range of new mathematical tools. Astronomers do not always have the language ready for that, and so they have to consult other fields of expertise to try to understand this. It is interesting because it does contain interesting information that we actually should look at. So, how does this work out in reality? Do we see some of these structures? So, just to give you an example of the filament in our universe. I mentioned earlier on the discovery of the Boötes void in 1981, and the Boötes void is still the most canonical example of a void in our universe. I would say that the local void, which I will show at some stage, is perhaps even more outstanding, but the canonical example is Boötes void. The canonical example of a filament is the Piscis-Perseus supercluster. And here you see it on the sky. And this is actually a map, a surface density map of galaxies that were observed with the Arecibo telescope. Now it was of course destroyed by hurricanes, but for decades it was actually the most powerful telescope to look for hydrogen in galaxies, in late-type galaxies. And in particular, for example, Martha Haynes and Riccardo Giovanelli made a huge effort towards mapping the distribution of galaxies in various regions on the sky on the basis of their H1 21 centimeter line. The great advantage was, if they could detect this, 21 centimeter gives you directly a wavelength, so you immediately would know the redshift, right? So it's much easier even than in the optical. You just look with your radio telescope, you see a line and you say, oh, it's 21 centimeters slightly shifted to that, that's the redshift. So that's what they did. And what do you see? You see here an enormous ridge. This ridge is over 100 megaparsecs long. Along that ridge, you see various clusters. A426 is the Perseus cluster. But you see other ridge clusters. Abel 347, 262, and it extends all the way up there. So you see this enormous ridge, but that's the ridge on the sky, right? Now, they also map the whole region. So here you see another one. So you see directly here that what I told you about. You see a filament connected to a filament, and the connection is right there in a clumping of clusters. You see also here an arm, and in between is a more tenuous wall surrounding these galaxies. Now, what they also did is look at the redshifts, and then it turned out that this is not just an artifact, it's actually a tube on the sky. And we're very lucky because this very close filament, a very prominent filament, not only is very prominent, and you could measure the filaments, but it turned out to be exactly perpendicular to the line of sight. So we get a beautiful impression of a filament stretching like this. And it's actually one of the closest ones. I soon have a map. So they looked at the galaxies here, and it was really like a tube. So since that time, we know that these filaments are real structures. They really elongated things. Now, nowadays, following up on this Bayesian reconstruction game, etc., we have a much nicer view of the viscous precious chain. This is the dark matter distribution in the same region. This is the viscous precious chain, and all the arms that you see around here is the implied dark matter distribution. You see the tube-like things, that's the highest density, that's basically the subfilaments in there. And that thing is actually the Perseus cluster. This is built on a map that was made on the basis of the so-called Bayesian approximation, and I will tell about that tomorrow. That followed up on the initial conditions that were inferred by Francisco Quintaura with this Bayesian inference technique. So this is the map of the implied dark matter distribution in the direction of viscous Perseus, following observations of the so-called 2-mass, 2-MRS redshift survey. So you see now how beautifully we are combining theory and observations into obtaining beautiful maps of the underlying structure. So now you may ask yourself, what now about this viscous Perseus chain? Right? I showed you the map. Now we can do complete cosmography. So here you see the viscous Perseus chain, but now it's basically twisted to this side, just to give you an impression of where we are. Here you see home. That's us. My student John Hidding put, with a smile, he put home in there, but it's us. So this is the real world. And you see each of the diamonds, that's a galaxy in the 2-mass survey. So you see the reconstruction is not bad. Eh? You see that the galaxies are really lying on the dark matter implied by this distribution. Now look at that. That's viscous Perseus. That's that prominent filament nearby. So what's the rest in front of it? Now it turns out that we actually are basically lying on the edge of a huge void, and on the other side of the void is the viscous Perseus chain. That's nice, isn't it? And we actually have a connection to the viscous Perseus chain. Here on the left-hand side, there's a prominent wall that connects us, the local supercluster, dominated by the Virgo cluster here, which is a flattened wall-like structure, via filaments going up over there. So now you know sort of the map of our local universe. In a sense, when you turn it around, I also have maps of that, you almost get a fear of heights because it's totally empty there. And then on the other side there is another structure. It feels like you're almost falling off a cliff. So steep is the density gradient, right? So we are here, and then suddenly bang, you have a void, and then on the other side, 50 megaparsecs on, is viscous Perseus. So this is the real world. Now, of course, it would be fantastic if we could study this real world and look and make, do something more than saying, look how nice, etc. Could we do real data analysis on such structures? Could we analyze them? Well, that's a bit difficult, isn't it? On Wednesday, I will be talking about it too. Do we have tools so that we can actually talk about how prominent the filaments are, what the distribution of their sizes is, what the mass distribution is, all these kind of things. So to that end, we are going to see the tools that we have been devising, and we, I mean the community, because there's a range of tools around, to basically extract the filaments, but in an objective fashion. So you're not allowed to say 2 megaparsec filaments. No, because, is that fair? We saw that they come in a whole range of sizes. So you will have to use a method that does not a priori assume a size or a shape. And you see here one of the tools. This is our own tool, the multiscale morphology filter / nexus. I will explain why that is. And you see that here in a dark matter distribution, we are in blue actually able to extract the filamentary network. And you see it's a branching network. So you see here the major artery connecting to a huge agglomerate of clusters. Think again of viscous Perseus here. This would be on a par with this, even though this is a random simulation. You also see that out of these main arteries are smaller filaments sticking in every direction. And it goes, branching goes on till smaller and smaller levels. So here you have these sub-branches branching off, and then smaller and smaller ones. And then inside the ports, you have the most tenuous filaments, the leftovers of the small vaults in the earlier universe. So these tools like this that are based on, there's a range of them around, and they usually are borrowed from computer vision techniques or other data analysis techniques. Usually the development of such methods is really interdisciplinary or cross-disciplinary work. So once we have that, we could basically look at the filamentary network at different resolutions. And you see here, for example, a simulation, and you see basically the cosmic web is repeating itself on different scales, almost as if it is fractal-like. Here you see again how that works out. So when you wonder, you have filaments here, like here, with the same tool set. We actually here show you the filaments with different colors. And the different colors you see here, and they are the sizes. So the blue ones are the small ones with diameters of 0.5 megaparsecs. And it goes up to the most heavy ones. And you see they are near the nodes. That's basically where you have the most heavy filaments, right? So this is basically the multiscale cosmic web. And the same thing you could do, for example, look at the voids. And here is a other prominent void in the local matter distribution. This is the so-called local void or Tully void. And you see again here is home. So this plane is our local supercluster. And you see that's a large void in the dark matter distribution. It's based on the same reconstructed initial conditions. So what about the connectivity of the cosmic web? Well, like I said, the filaments and the walls, they're all connected. So here, with the same tool, we looked at the filamentary network and we looked at the walls in a part of a simulation. And by turning this around, you basically see how the connections of the cosmic web work. So you clearly see that the filaments are connected up in a network. So it's a complete percolating network throughout the universe. And then you see that those filaments appear to be the boundaries of the membranes, of the walls in this distribution. And if you look well, you see clearly, once it turns, you see that inside here are the cavities, the voids, right? So it's a complete network of a web-like structure, and everything hangs together. Okay? Like you see here, zoomed in, you basically see that here's focusing in on the void. In red here you see the filaments. You see the filaments connect up at the nodes. Here you see the nodes, and you see it sticking out, and you see that filaments are basically the boundaries of the walls. If you, by the way, if you're ever interested in 3D printing, which is quite nice, so that's what we so now and then do our spare time, print these things. So I have a couple of these things on my desk standing. So you can get the so why is the cosmic web interesting? For a range of aspects of the cosmic mass distribution. For various people, it will be interesting for various reasons. First of all, it's clear that it is a very characteristic stage of cosmic structure formation. It's the first stage of structure formation in the universe, following the initial circumstances. Also, not surprisingly, in different cosmologies, you will get a different filamentary network and different voids and different walls, but they are less prominent. Actually, by now, there's a huge amount of effort using the voids to infer very stringent constraints on cosmological parameters. It turns out that the size distribution of voids and the shapes of voids is very sensitive to the nature of dark energy and other cosmological parameters. So there's a whole range of efforts for the upcoming large surveys to use voids, for example, to infer limits on on cosmological information. Of course, in that case, you really need these objective criteria to select these structures. And then finally, we will also hear that in lectures on the influence of these cosmic environments, of the filaments in the walls, on the formation, evolution, and properties of galaxies. The most prominent one of which is the rotation of galaxies themselves. They get their spin from the same tidal forces that are forming filaments. But there's a range of other aspects where you see that the environment in which galaxies form is actually influencing their properties. So if you are someone who is interested in the evolution and formation of galaxies, also that you will have to look at. So how to understand the cosmic web, how to put it in perspective. Everything, of course, depends on our understanding of where this structure came from. That is, on the dynamics of the structure formation process. It's not that complex. The way this structure is formed is simply gravity, with, at the later stages, some gaseous processes, but most of it is just gravity. Gravity is the agent in which the cosmic web is formed. But why then does it end up like the cosmic web? Because you might argue, if you take a primordial peak in the mass distribution, it should collapse and become a clump, and that's about it. Well, apparently not. Apparently, it's much more complex than that. You get a web-like structure. So it all starts with the primordial universe. The primordial universe, here you see a map from the WMAP satellite, is a Gaussian field of very minute density and velocity fluctuations. Density fluctuations are not more than 1 in 100,000. It's mostly just uniform, except for some minor deviations of 1 in 100,000. Still, that's enough. If you have dark matter, by the way. If we would not have dark matter, these fluctuations would have been too small to form anything like a galaxy. Dark matter is essential for our existence. So what happens, of course, is that this uneven, minute distribution of matter causes an inhomogeneous force field. That is, if you are close to the mountains and the ridges in the landscape, locally the gravitational force is just a bit stronger than the one on average. While in the voids, the gravitational force is slightly less than average. That means that you will get a runaway process. And the runaway process goes as follows. You start off with a slight uneven mass distribution. That translates into a slight different inhomogeneous force distribution. This is the force with respect to the overall gravitational force of the universe, the one of the frequent Robertson-Walker universe. And you clearly see that near, for example, a large overdensity like here, the arrows are pointing inwards. They're pointing towards that little hill. While the ones near the underdense region are pointing slightly outwards. Mind you, this is with respect to, so it's not a repulsive gravitational force, it's just slightly less, right? So it's always attractive, but the matter in the voids attracts slightly less, because there is slightly less, than in the overdense regions. That translates, of course, into migration streams. Mass starts to move. We see the motions actually in the galaxies. You see that the mass is moving towards the high density regions. So the high density regions actually get a higher density. And the low density regions, their matter starts to stream out. So they get less density. So the contrast grows. So the deviations in force become even more prominent. And you get a feedback loop, which we call gravitational instability. That's how the structure formation process goes. Notice that I did not yet explain to you why a weblike structure. There comes the second gravitational instability. We'll get to that in a moment. So the typical thing that you see is an initial mass distribution. This is at a, well, not that high redshift, but you see it's not yet prominent. You see it's mostly a mountain landscape with some underdensities and some overdensities. But by today, it looks like this. Right? So you see around the mountain, a total clump appeared, a node of the network. And when you look at the connections, you would not have guessed yet in the mass distribution, right? That actually it would be arms sticking out in various directions. In the arms, you see a lot of clumps. That's the hierarchical distribution. It started on small scales. They, you see the small inhomogeneities, they collapsed locally, and then they finally ended up in this filamentary structure, right? So, yes, this is the result of millennium simulation, and it clearly shows from the simulation that the web is a natural outcome of gravitational evolution. Okay, but we want to understand why, right? Because otherwise we don't get further. Now, how does this tie in with the hierarchical evolution? For that end, it's best to show you a movie. And it's an old movie. It's an old simulation. It's not a super duper simulation. It's a simulation from 20 years ago, but it illustrates nicely what happens. Look at the number on the top left-hand side, redshift 20. Way even before what JWST is going to see. And you see the mass fluctuations are minute. And then gravity sets to work. Follow the counter. First it goes slowly, and gradually you now start to see the filaments appear. And look, they're small. And the void regions you see too, but they're small. And look, the bubbles start to merge into ever larger bubbles. And you see the filaments, exactly what I showed you before. They start to string together into ever more massive filaments. So here you see that actually the cosmic web results from gravity. And it actually does so in this hierarchical way, with small structure stringing up to ever larger structures, with at the nodes the clusters. This is what you have today. This would be a supercluster, and etc. This would be the large voids like code, like the Otis void. But you see, it illustrates you the hierarchical way and the natural way of mass to contract because of gravitational instability, but not in an isotropic way like this. But the most prominent feature is that it actually contracts in anisotropic ways. It forms filaments and walls. So why would that be? And here comes the second aspect of gravitational instability. It has everything to do with what we call tidal forces. So here you see a map of a large simulation, and on this map we actually calculated the local tidal forces. What does that mean? You look at a mass element and you wonder what would be the gravitational force because of the inhomogeneities on this side and that side. And what's the difference? The difference, of course, means that that mass element in one direction would be contracting, because there the gravitational force difference is larger than in another direction. It's not unlike the force of the moon and the sun on the oceans of the earth, right? It's the differences in force between one end and the other end. That's all there is. And this is the map in black bars of the tidal forces, so the differences in force for the direction in which it is stronger than average. So it starts to contract in that direction. I could also have done it in the dilation, because one direction, at least one direction, it will move in that direction, and the other one it will contract. Now, what do you see? The interesting thing is, when you look along that filament, you see that all those bars are nicely lined up. They're not random, they all systematically line up. For those of you who know about gravitational lensing, you may have seen these things actually in projection. You see here a clump, and then you actually see that the pattern is actually like a ring around it. You may recognize it, but this is three-dimensional, by the way. So what will be the effect? The effect will be that there will be contraction in that direction. So the thing will not only collapse, but it does so in a preferred direction. That's why you get the filaments and the walls. The walls means there's a preferred direction in this way that you will contract. With the filaments, it's going to do along the two directions. You will only get a clump when the overdensity is so high that you will also contract in the third direction. But it's not normal. The most normal way is actually the elongated filamentary pattern. That's why you get the filaments. So the second aspect of gravitational instability, very often not mentioned, is the anisotropy of the force field that naturally shows up in the initial conditions. And here you see a very sparse simulation of this is a part of the initial distribution where you have a clump over here, and you see that in there you get a bridge, and that in time will form a filament. This is actually this other aspect of the story. There is no free lunch. If you say here that you want to have a force field that is forming a filament that's contracting in one or two preferred directions, you will have to find the source of this anisotropy. It cannot just come out of nowhere. And actually, for those of you more in the context of electromagnetism, may recognize this. If you have a quadrupole at a certain location, isn't it that you always have two poles at the other end? It's a natural circumstance. And here you see, I specified here a tidal force. This is the complex feature. For those of you who are interested into what this is, you may recognize the 1/r third component for the quadrupole and stuff like that. It's detailed, but important details if you want to translate it. You have the anisotropic force field here. Hey, I get a clump there and there. And what are those mountains on the other sides going to do? They are so strong that they contract towards clumps. You see them here and there. So the connections are automatically implied by the mass distribution. If you have a filamentary contraction, you will find at the edge two clusters. Right? So that's the connections. And this is the anisotropy of the gravitational collapse. I'm almost there, Paul, so then so this will be the the thing. So basically, if you have an anisotropic feature, you always get that there is a faster contraction along one axis than along the other axis. And this also is a runaway process. So it's not only that you get this contraction, it's going stronger and stronger as that other gravitational instability. Why? Well, the contraction along that direction goes stronger, so it contracts faster along that direction than along that direction. But that automatically means that along the shorter axis, the anisotropy actually grows. It becomes stronger in this direction than the larger direction. So the filamentarity is amplifying itself. It's not resisting, it's actually amplifying itself. It's a second gravitational instability that is not usually mentioned. And actually, where then, in the end, was the source of all this anisotropy in the initial circumstances? And here is something, this is a work that we've been working on over the past time. Tomorrow I will tell more about it, but it illustrates a very interesting finding, and we had never realized it ourselves until we saw the maps. So here are maps of the initial mass distribution in a Gaussian density field, of the initial potential field, but although that's almost not there, and of the anisotropy in the force field, the tidal force field. So this is the map that you usually see. That's a Gaussian fluctuation field, right? I showed you the Millennium simulation and you saw the local mountain, and then in the end we ended up with a clump with arms sticking there. So where are these arms coming from? Why is the force field anisotropic, and why these arms? Where is it coming from? It was hard to see that in the density field, isn't it? So could it be the gravitational potential, because that's dynamically more important? That's what you see there. And you see it's also rather blobby. It doesn't really tell you anything in that sense. Yes, it tells you that here there's going to be contraction. It's an overdense region. There's an underdense region. But then we looked at the Hessian of the gravitational field, the second order gradient of the gravitational field. d2 phi, dqi, dqj. You know, that's the tidal force, right? The difference, the gradient of the force. The force is d phi, dq. So the gradient of that tells you how it differs. And then you see it's actually a 3×3 tensor. So it's a combination of the anisotropy and of course the orientation. So take out the orientation and look at the anisotropy. So look for the eigenvalues. It's mathematics, but surely you can follow this. Here's the maps of the eigenvalues. Now, isn't it beautiful? The cosmic web is already there. In the initial Gaussian density fluctuation field, if you look at the implied tidal force field, this is the primordial field. This is not the evolved one that I showed. What do you see? You see the lanes, the connections. It's all there in the initial circumstances. And I think for today, that's a proper way to stop so that tomorrow we can follow up with dynamics and structure. The cosmic web, the main lesson. The cosmic web was formed by the tidal force field, and it was already there 13.8 billion years ago. Okay, thank you for today.
And now questions, please. Thank you for the nice talk. I'm just curious to know how the substructure formation occurs within the forest. So is it because of the filaments are breaking up and some of the clusters are somehow being ended up in the voids, or because single galaxies are somehow being tidally disrupted from the filaments, and they are getting agglomerated in the within the voids, and then they are forming the substrate?
Yes, so you mean the clumps inside the filaments?
Yes.
Where did they
No,
come?
within the voids.
Oh, within the voids?
Yes.
Well, the voids, as you saw in that simulation, and on Wednesday I'm going to talk more about it, the voids actually also merge hierarchically. So the way you have to look at it is almost like a soap salt, right? If you do the dishwashing, you see it, you see the small bubbles, and if you wait for a long time, you see that the bubbles merge into ever larger bubbles. And in the end, it's only a few large ones. It's almost like that. The forces are slightly different. Now, what will happen? You saw that. You saw the small voids, but in between the small voids, you have, of course, mass concentrations. And in those mass concentrations, you form small blobs, right? It's not a lot of mass, but enough locally to win gravitationally and form a small clump. So these small clumps are actually what you expect to find in the voids. It's not a lot of them, but they're there, and you expect them to be there, and you see them. Actually, we had a survey, multi-wavelength survey called the Void Galaxies survey, where we just looked into directions of voids in the Sloan survey, and sure, you find these small blobs. Although, admittedly, there are fewer than what the theory suggests. That's an item that Jane Peebles is constantly emphasizing. Everyone sings Hallelujah of Lambda CDM. But one of the things that it has difficulty with is explaining why there are so few little blobby galaxies in voids. There should be many more. But that's a detail that is still not completely understood, but it will fall. I mean, what you saw is voids are not unstructured. They're not empty, and that means that you have local density inhomogeneities, some of which collapsed into small galaxies.
And the second question I have, I'm curious to know if any people have managed. So, for example, one of the problems in observational astronomy is we have along the line of sights, there is source confusion. There are a lot of galaxies, foreground galaxies, background galaxies, because of which we have difficulties getting photometry and spectroscopy of our targets. So, if we are setting at one end of, let's say, a local world, and through the world we observe sources that are at the end of the other world. Have such work been done before?
Yes, there is no real problem with that, but there are other practical problems, observational problems. So you're, talking from an observational perspective, and who here knows of the fingers of God? Yeah, so at least many of them you do. So you could imagine that you have a void, and then on the other end is a huge cluster. And these clusters in redshift space are going to be stretched, right? They're going to be fingers of God. So they're sticking way up into the void. So how do you know whether this is a galaxy belongs to the cluster or in the void or something like that? That's pretty damn difficult sometimes. So, for example, when we did our Void Galaxy survey, that's 10 years ago, we did it in a very rude way. We said, whenever there's a cluster over there, then we throw away the void. We don't look at it because we don't want to have that confusion. But of course, at some point, you want to do it all. And then you will have to deal with these redshift-based distortions. And that's a much more serious matter.
Thank you.
Any question?
Thank you for the lecture. So, we saw that the formation of this cosmic web is due to the dark matter in our universe. And every time when we speak about early universe, we speak about formation of matter, baryon matter in our universe. So, when dark matter arises in our universe?
The dark matter was always there, except, well, when I say always, as far as we go, right? At some point, matter should have formed. At some point, also dark matter, but as you know, we don't know what the dark matter particle is. So we actually don't have a clue. When it's a particle, we don't even know for sure it's a particle. When it's a particle, when this thing emerged. But there are so many mysteries in the early universe that I cannot say about it. You know, the atoms, the matter that we exist on, we're basically remnants, right? Because actually, as far as our understanding of high energy physics goes, it's perfectly symmetric in matter and antimatter. But there has to be a slight asymmetry that caused in the end for matter to prevail. So, the surplus of matter finally became us. That's with respect to the atoms. With respect to the dark matter, I don't have a clue. But as far, because we don't know what the particle is, but as far as the story goes here, we start the story at some point, redshift 1,000 or 10,000 or a million. Dark matter was there, and it always was the dominant part of gravitationally of the matter. So when you talk about the early universe, the atoms and the photons and etc., cosmic microwave background, on the background was the dark matter, and the dark matter was actually the dominant gravitational component, although it did not contribute to the pressure. And the pressure is what we see in the sky, right? It's the sound waves and stuff like that. So that's the atoms and the photons at work. But underneath there, dark matter was always there. You could almost say it was already excavating the potential wells into which the atoms were going to fall.
Okay, thank you.
So you spoke about density perturbations led to structure formation, and we also saw that dark matter structures, like a cosmic wave made of dark matter. So the dark matter cosmic wave must have had an evolution of its own, right?
Yeah.
And you said that density perturbations wouldn't have been such a strong effect if dark matter wouldn't have been there.
No, we would not even have been there.
Yeah, so there must have been a dark matter evolution of the cosmic wave of dark matter, and that must have preceded the density perturbations of the regular universe. I didn't understand this part, that where does it line up chronologically? Because
what we have to understand, so if you look at the pre-recombination universe, right? So then the universe is filled with photons, atoms, or protons and electrons, and dark matter. Now, the protons, electrons, and photons are completely coupled in the pre-recombination universe, and they exert pressure on, the main source of the pressure is the photons, but they are coupled because of that. The dark matter doesn't care about the pressure, and it is already much more evolving gravitationally than those atoms and photons can do. So they can only go up and down. That's the sound waves. But the dark matter doesn't care. It goes on with its gravitational evolution.
So you say that there's this gravitational evolution of dark matter first into a cosmic.
Yeah, in the pre-recombination universe, the dark matter doesn't care about that pressure. It's the atoms and the photons that care about the pressure. So the mass fluctuations in the atoms cannot evolve in the pre-recombination universe because the pressure is basically holding it up. The only ones that can evolve is the ones that are in the pre-recombination universe. What was it, 10 to the 15 solar masses, because that's larger than the Jeans mass at that stage. But the Jeans mass is huge because of this enormous pressure from photons. So only those very largest atomic perturbations can slightly grow. But the dark matter doesn't care. It goes on all the way. It doesn't, for dark matter, the Jeans mass is 0. Just falls in. There's nothing holding it up.